Hello. Just send a quick message to everyone. I think I haven't done that yet. The webinar has started. Okay, so okay. So how many people do we have? Just 4. Okay, that can't be good. So let's hope some more people join. In terms of we've marked your work, and it's looking like the pass mark for maths is going to be approximately 60%, and the pass mark for physics is going to be about 45%. I can't promise that, but this is what we're looking at. Okay, so if you scored above 45, well, if you scored above 50% in physics and above 60% in maths, I'd say you're most likely in. Okay, so this is the entry criteria for this year. It's not very different from last year, slightly higher. Okay. Most of them have been returned. If you haven't seen it yet, if it hasn't been returned to you, then it will be done very soon. And there's one student that we cannot return for some reason. We can't return. We'll contact that student saying that we can't return your work, but your score is such and such. So tomorrow you will receive an email with your scores and the decision whether you're in or not. Okay, so and with the year 13 is quite simple. With the year 12, it's a bit more of a hassle. So have all of you been able to access the assignment? Have you seen the assignment? This is the physics assignment 2. This is on gravity. Okay. Is there anyone who doesn't know where to find physics assignment 2? Is there anyone who doesn't know where to find the assignment on gravity? No one. Okay, brilliant. So we're going to talk about gravity today. And first we start with the gravitational force, of course. Newton's universal law of gravitation. Have you done this in school? Yes or no? Have you done this in school? Yes or no? Have you done law of gravity in school? Ooh, very nice. Okay, so just a quick reminder that if you have two objects with mass m1 and m2, any two objects in the universe attract to each other with a force called the gravitational force, the force 1 from 2, and force 2 from 1. And if the distance between the centers of the objects is r, then the force is equal to g m1 m2 divided by r squared. And usually we put a minus here. The minus simply means that the force is acting in such a way as it is trying to decrease the distance between the objects. That's why we have minus. Okay, so it's trying to decrease the distance. If, for example, an electrostatic repulsion force, if you have two positive charges, for example, the force is going to be positive plus k q1 q2 divided by r squared, because they're trying to push apart. The force is trying to increase the distance, and that's why it is positive. Okay. Problem 1 is quite simple. How does the fact that the astronauts on the ISS, International Space Station, are weightless confirm that the gravitational force is proportional to the mass of the object? Okay. So if you imagine that this is the planet, this is the planet Earth, and there's the space station. This is the space station. Not a very accurate representation, but and then inside the space station there's an astronaut, and the astronauts are weightless. Why do we say that they are weightless? Are they weightless? First question. Do they have no weight force? No. Can somebody elaborate? Can somebody speak up, perhaps? It's this time of the year. And explain why you think so. There is some attraction to the Earth, of course. Unless you are an infinite distance away, you always have a weight force. Very good. Very good. Well, not necessarily, by the way. If you're in the sweet spot between the Earth and the Moon, for example, between the Earth and the Moon, there is a sweet spot somewhere here where there's no gravity, no weight. So if you found yourself right here, this would you can find. But yes, because you are inside the spaceship and there's weight. The weight is the force that is attracting you to the Earth, of course. And there's a force on the spaceship as well. This is the weight of the astronaut, and this is the weight of this spaceship. So the spaceship is, well, this ISS, International Space Station, the weight of the ISS and the weight of the astronaut. Now, the Earth has mass m, let's call it me, and astronaut has mass ma, and this has mass miss. The force, the gravitational force, causes acceleration, causes centripetal acceleration. The weight causes centripetal Centripetal acceleration. And you know that F is equal to ma. So for the astronaut, the astronaut, the mass of the astronaut times the acceleration of the astronaut is equal to g mass of the astronaut, mass of the Earth, divided by r squared, the distance. And for the ISS, the International Space Station, mass of the ISS, acceleration of the ISS is equal to g mass of the ISS, mass of the Earth, divided by r squared. And we can cancel ma here, and we can cancel miss here, and we have that ma has miss. So, and this is true because what did it say? Ma. I'm speaking nonsense. Not the mass, acceleration, of course. Acceleration of the astronaut is equal to the acceleration of the ISS. And this is because force is proportional to mass of the object. In other words, the acceleration of both objects is the same because the force is proportional to mass. And yeah. And they have the same acceleration. That means there's no contact force. There's no contact force between spaceship, the ISS and astronaut. That is the reason. So if you look at a human on Earth, if you're sitting in your chair, so this is your room, and you're sitting in a chair, you have the weight force acting downwards and the normal reaction acting upwards, normal reaction force. Now, if you're in a spaceship, in the ISS, this is your room. What's different? What's different? You have the same weight, well, pretty much the same weight. But there's no normal reaction. Yes, because you're not touching, you're not pushing against anything. So the sensation of being weightless is not weightless. It's not actually, you're not actually weightless. You have the same sensation. This is equivalent if you go to a swimming pool. Does anyone like diving from a height into a swimming pool? And you jump. And when once you're falling, you're in free fall. You have the weight, but there's no normal reaction. So the sensation of the astronaut and the sensation of a person jumping off a diving board is exactly the same. Okay. So the astronaut is constantly falling, just like you are, but you're falling not constantly. You're constantly falling for some time. So if you're ever in a swimming pool, well, don't take the highest one, but 2-3 meters is absolutely fine. It's very difficult to hurt yourself from 3 meters. So go for it. More than 3 meters, it hurts. Like, honestly, I've jumped from 7 meters and it hurts if you don't know what you're doing. But yeah. So weightlessness, weightless is not the correct term. It's normal reactionlessness. And it's a copyright by Vlad. Okay, anyways, let's move on. Derive the expression for the gravitational field. Use it to estimate the mass of Earth. So the gravitational field, the definition of gravitational field is the mass per, is the force per unit mass. So field is the force per unit mass. Okay, so if you have a planet, the planet has a gravitational field around it. The field is in an inwards direction. By the way, I have to mention that I have done at least 1 or 2 webinars on this topic last year. So I invite you to watch these if you have questions afterwards. So we have the gravitational field. So the strength of the gravitational field. The gravitational field is G. G is the gravitational field. And by definition, G is the force per unit mass, which is placed. So if you put a mass here, there's a force on that mass. There's the force. And we know that the force is equal to G m mass of the planet, mass of the object, mass of the planet, divided by r squared, where r is the distance between them, from the center, from the center of the planet to the object. And if you substitute that in here, this gives you G m over r squared divided by m cancels, and you are left with G m over r squared. Right, so that's that. That's the gravitational force. The gravitational field, sorry. The gravitational field around a point mass or a spherical. So gravitational field strength is Gm r squared multiplied by, well, sometimes we say multiplied by r. So the unit vector in the direction of the object. The gravitational field from a gravitational field from a point mass or spherical mass. Okay, spherical uniform distributed mass, such like a planet. So let's look at this question. At a point outside the Earth and a distance x from the center, the Earth's gravitational field is about 5. At the surface, the field is about 10. Okay. So at a distance at a distance x from the center of the Earth. Distance x. Gravitational field G1 is 5 newtons per kilogram. And at the surface, gravitational field G2 is 10 newtons per kilogram. Find the radius of the Earth in terms of x, r. This is very similar to one of the problems from the assignment. Okay. So what do? Well, we say that G1, the formula is Gm, where m is the mass of the Earth, divided by x squared, and G2 is equal to Gm over r squared. So from here, G1 x squared equals to Gm, G2 r squared is equal to Gm. Because Gm and Gm, you can make them equal to each other. So G1 x squared equals to G2 r squared. Therefore, r is equal to square root of G1 over G2 multiplied by x. Yeah, you can rearrange that. So square root of G1. G1 is what, 5? 5 over 10 x, which is x divided by root 2. So this is the answer, root 2. And this question is from Isaac Physics. Highly recommend using that resource. It's free of charge. It's made by Cambridge University. Honestly, no idea. I'm as far away from math as I can. I can be. So yeah, I'm not sure. Okay. Does this make sense? Does this make sense? How well do you understand problem 3 on a scale of 0 to 10, please? Very good. Very good. So, before we do problem 4 and 5 and 6, actually, you know what? I'm going to switch them around. I'm going to this one, and this one. Let's put it this way. I want to explore what happens. No, like outside the planet is easy, right? Outside, if you're outside the planet, life's good, right? I'm more interested what's going on inside the planet. So gravitational field, the field outside the planet. So for example, you have a planet. And if you draw an axis, this is the radius of the planet. So this is a graph, and r is the distance from the center of the planet, and this is the gravitational field. And we know that the gravitational field is equal to gm over r squared. So imagine, so for the Earth, for example, the gravitational field at the surface is 9.81. Yeah, so let's call it G0. So for the Earth is 9.81. And as you go away from the Earth, it behaves as 1 over r squared. It's proportional to 1 over r squared. Can somebody tell me what would the gravitational field be if you are at the center of the planet? G. Okay, we have two options. And some people have posted both. Both options. We have 0 and we have infinity. Okay. And the rest haven't decided. Well, according to this formula, yes, it looks like it's going to be infinite. But this doesn't look like I mean, if you think about it, if you go to the center of the planet, would it be infinite? Would the gravitational field, as you go deeper into the ground, does the gravitational field increase? Why do we have a gravitational field in the first place? Ooh, Beata. Yes, very good. Very good. Because of the mass of the planet. The mass of the planet pulls you down. So if you're standing here, the Earth pulls you down. It doesn't pull you just down. It pulls you in all directions. But all of these directions are sort of down, have a downwards component. So yeah, it's pulling you down. But if you're at the center of the planet, you're being pulled equally in all directions. Because the mass, you're attracted to mass, the mass of the planet. Therefore, there's no gravitational field in the center. And that's kind of a interesting thing, because this formula, it kind of contradicts the formula. So what's going on? Why does it behave like this? So one more thing. If you are inside a hollow shell, so imagine the planet is a hollow shell. It's pretty sure there are multiple fantasy books about the moon, for example, being a hollow planet, and inside there are people living. Okay, hollow shell. It turns out, and I won't do the maths, but if you are inside the hollow sphere, let's look at this part. So this part pulls you this way, but this part pulls you that way. So even though this part is further away from you, there's more mass. M1, M2. It's further away, but there's more mass. And here it's closer, but there's less mass. It turns out that inside a hollow shell of uniform density, the field is going to be 0. Gravitational field is going to be 0. Basically, you're being pulled equally in all directions. Even if it is a big shell. So this is something I won't rigorously prove. This is proved but with integration. We need to take a surface integral of the parts of the sphere, and that's not something I'd like to do right now, and not something well beyond. But let's establish that this is true. Let's assume that this is true, and believe me, it is. You can find proof of that fact online. Okay. So, what does it mean for us? This means that if we are inside the planet, and let's say we are here, you are, this is you. You can say, well, I am inside the planet. Or you can say, wait a second, I am actually inside a hollow shell. I'm at the edge of, I'm the inside of the outer shell. And I am outside of the inner part. So this is part of the Earth that is closer to the center than you. And the outside is a hollow shell. So the outside does not contribute to the gravitational field. How well do you understand what I'm talking about? Have I lost you? So on a scale of 0 to 10, please let me know how well do you understand what we are doing right now. Okay. Samadrito, do you understand that if you're inside a hollow shell, the gravitational field inside is 0? Do you understand what I mean by that?
I understand what you mean, but I don't know why that is true.
Okay, good point. Let me draw another example. Unfortunately, I can't show you the rigorous proof that this is true. But let's say you are here. Let's say you're somewhere here. And there's part of the sphere, the mass is located only at the edges, right? There's part of the sphere that pulls you up, and there's parts of the sphere that pull you down. Now, this part of the sphere pulls you down. And the rest of the sphere is pulling you up. Right? So this is you. The blue part of the sphere, of the shell, is pulling you up. And the red part of the shell is pulling you down. But it turns out, because the blue shell is so much bigger, but it's further away, and the force is proportional to mass, m2, m1, m2 divided by r squared, and inversely proportional to the square of the distance, it turns out that these two forces are exactly the same. So F1, that is pulling you up, and F2, that is pulling you down. And this is the same in all directions. In any direction that you take, you will turn out that the forces are balanced. In other words, inside a shell of uniform density, there's no gravitational field. Does that make more sense, Madrito?
Yes, but does this depend on the size of the shell, or is it true for all sizes, like even for quantum sizes, for example?
Well, we're not going quantum because Newton's law of gravity doesn't work on a quantum level. So how can we discuss that?
Oh, okay.
Right. We're talking about any shell which is less than less than astronomical size and more than an atom. Yeah, like significantly bigger than an atom, significantly less than a galaxy. Okay, let's put it this way.
Okay.
The maths is not very complex. It's just long. It's just long. It will take us half an hour to go through that, to go through the maths. It's not that complicated. So you have the full so if you dig a hole, a big giant hole in the earth, I don't know, 3,000 kilometers. So if you're 3,000 kilometers underground, so it's about halfway to the center, 3,000 kilometers, you can say, well, I am sort of inside a hollow shell. I'm inside the hollow shell. This is my hollow shell. So you're right at the edge of the hollow shell. At the same time, the only thing is attracting you towards the center of the planet is this part. So if you are inside the planet, the only thing that is pulling you towards the center is the part, this middle part. Mathematical proof. Is the so just to clarify, inside any shell of uniform density gravitational field associated with zero, this field from that shell, of course, the gravitational field from that shell, because if you have an external gravitational field, then obviously it is not zero. Okay, because otherwise you could just get into a giant football and be weightless. It doesn't work, right? But if you are in deep space and there's no external gravitational field, then yes, then this is true. So yes, the only thing that's pulling you down. So let's say, suppose density of planet is rho. R is the radius of the big sphere. R small is the radius of the small sphere. Okay. So mass mass of Earth is going to be 4/3 pi r cubed. That's the volume of the cube multiplied by density, right? So it's volume times density. Mass of Earth is volume times density. Mass of red part is 4/3 pi r cubed rho. Okay, that's the mass of this part. The force from field from red part is equal to g, gravity, and it's equal to 4, it's equal to g mass m over r squared, which is g 4/3 pi r cubed rho divided by r squared. This is r. So it's 4/3 g pi r rho. Okay. I don't hear the sound of your minds being blown. G is 4/3 g pi r rho. What is the significance of that? What is the significance of that? Come on, anybody, anyone.
The field is directly proportional to the radius of
Exactly.
the
Exactly.
electron.
Field is directly proportional to the distance from the center. And this is like a woo, wow. How come? So outside the planet, it's inversely proportional to the radius squared. But inside the planet, it's linear. So gravitational field inside the planet, we go back to this graph. It's like this. It's a straight line. It's directly proportional. Directly proportional, and then outside the planet is proportional. So inside it's proportional to r, and outside it's proportional to 1 over r squared. So first, the gravitational, if you start from the center of the planet, as you go away, the gravitational field increases and then decreases. It increases and then decreases, and that is great. So there's a question in the assignment. There's a question in the assignment, which is an example. And it goes like this. There's a tunnel that is drilled through the center of the planet from the North to the South Pole. And there's no air resistance. You drop a stone, you drop a rock down from the edge of the Earth, from the North Pole, to the North Pole to the South Pole. Describe the motion of the rock and figure out how long will it take it to reach the center of the planet. So describe the motion How long will it take to reach the center of the planet? Okay, now we know the acceleration of the rock. Acceleration is equal to g. We know the distance, r is equal to 6,400 kilometers, roughly. We know the acceleration, we know the distance, we know that the initial velocity is 0. Can we use SUVAT?
Yes.
Okay. Well, the correct answer is no. Can somebody explain why?
The force will vary.
The force and hence the acceleration will vary. You can only use SUVAT only if the acceleration is constant. Here the acceleration is not constant, therefore you can't use SUVAT. And if you draw, so let's say you are here, you draw a force diagram. So there's only force of gravity. Force of gravity is equal to mg. And when you are inside the planet is the mass of the rock multiplied by g, which is 4/3 g pi rho r. Have I made a mistake? G pi rho r. No, I haven't made a mistake. Okay. 4/3. And we know the mass of the Earth. No, that's fine. I don't think we need anything else. Right. So in other words, mass acceleration is equal to m 4/3 g. Well, and of course we need an x-axis. So let's put it this way. Let's make this the x-axis. So when the stone is at position x, so this is 0. This is the center of the Earth. This is the current position of the rock, and the force, so x, but the force is going in the opposite direction. If the displacement is up, the force is down, so it's minus. So ma is minus m 4/3 g pi rho x. In other words, m cancels, and you have acceleration is equal to minus 4/3 g pi rho x. Now, at the surface of the Earth, g0 is equal to 4/3 pi rho r, where r is the radius of the Earth. In other words, and g, of course, 4/3 g pi rho can be written as g0 divided by radius of the Earth. So I'm going to plug that in here. A is equal to minus g0 divided by r multiplied by x. Does anyone recognize this equation?
It looks similar to the acceleration in a pendulum.
Exactly.
Yeah.
Simple harmonic motion. Thank you. Thank you very much. Acceleration is minus omega squared x. Therefore, omega squared is equal to G0 over R. Omega is equal to square root of G0 over R. And omega is 2 pi divided by T equals G0 over R. And therefore, the time period is 2 pi square root R divided by G0. It's a simple harmonic motion with period T. But a period in simple harmonic motion, so the rock will travel to the center of the Earth, then to the South Pole, then back to the center of the Earth, and back to the North Pole. And that is one period. How long does it take to reach the middle? Well, it's a quarter of a period. It takes T over 4 to reach the center. So it will take T over 4, that's a quarter of a period, to reach the center. So T over 4 to reach the center. So T is equal to 2 pi square root of R, a radius of the Earth is 6,400,000 meters, divided by G, well, 9.81. So we can work it out as 2 pi multiplied by square root, fraction 6,400,000 divided by 9.81. You get 5,074 seconds, 5,074 seconds, which is divided by 3,600, 1.4 times 60. 84.6 minutes, 84.6 minutes. And T over 4 divided by 4, 21.1 minutes. So it will take the rock 21 minutes to reach the center of the Earth, 42 minutes to reach the other side of the Earth, and about 84 minutes to come back. Okay, this is assuming, of course, there's no air resistance, because if you calculate the maximum velocity using, Vmax is the amplitude multiplied by omega, it will turn out to be quite large. Okay. Anyways, 84 minutes to reach. Well, 84 minutes sounds like something familiar. Sounds like something familiar. Let's check how long it, ISS period. ISS period is about 90 minutes. 90 minutes, which depends slightly, but it's about an hour and a half. It's about an hour and a half to reach, to travel, and it's not a coincidence. The period of the ISS is slightly more because it's not at the surface. It's slightly above. It's 400 kilometers above the Earth, in fact. So it has a radius not 6,400 kilometers, but 6,800 kilometers. So it's slightly bigger radius. And if you do the calculation for a bigger radius, you won't get that the period for the ISS. The ISS you have the time period is, sorry, the radius is approximately 6,800 kilometers. And that means that it's 2 pi square root 6,008 divided by 9.81, which will give you, should give you about 90 minutes. So 2 pi multiplied by square root fraction 6800000 divided by 9.81. $87 minutes. Well, closer. Perhaps the radius of the Earth wasn't taken accurately, but anyways, it's roughly that. Now, ISS period. What else? What else was there? Oh, yeah, ISS. I really recommend ISS Tracker. You can find where the current position of the International Space Station is. No, not this one. Current position of the ISS here. So it's near Mexico. Okay, but sometimes when you look up into the sky, you can actually see it. It's like a bright star moving across the sky, and it's really fascinating to watch. It's best viewed in the summer, just after sunset. You can see it quite brightly if it's above your head. So you just need to check: is it above your head? Sometimes I was like, I wish the International Space Station was above my head. I look up and here it is, and I check the tracker. Oh, yes, it is. So yes. I recommend some ISS spotting. It's quite fascinating. Right. Okay, so these are orbits. I'm going to reshuffle again. Don't want to do orbits at the moment. So derive the expression for gravitational potential energy and the gravitational potential. So I know you've learned that gravitational potential energy is mgh. But there's a few problems with this formula. First of all, what is h? So problems. First, what is h? If I say, what is the gravitational potential energy of this orange? Well, I would typically measure it from, from the table. But why am I measuring from the table? Why am I not measuring from the floor? And if I am measuring from the floor, why am I not measuring from the street level or the sea level? Like, what is h? This is not an obvious question. We say gravitational potential energy is relative to the starting point. To what are you measuring it in relation to? It depends on what is your reference point. Yeah, usually we say delta H here, and that makes sense. And then we talk about change in GPE. That solves the problem, yes. But the second problem is that only true if G is a constant. But as we have already seen, G is not necessarily a constant. So if you're talking about large displacements, it's not going to be constant. So let's find a better formula for the gravitational potential energy. Gravitational potential energy is the energy needed to move a mass from infinity to a given point. So what does it mean? Well, if we have a planet and we have an object, and the mass of the object is m. The question is, what is the gravitational potential energy of that object? Well, it's the energy needed to move it from infinity to that given point, which is, let's say, a distance r away from the center of the planet. The planet mass m, by the way. So what is the work done? It turns out that it doesn't matter how we move. We can move in a straight line, or we can move along this strange path. So we need to move the mass from infinity to point P. So moving from infinity to P. Okay. Let's look at a small part of the track. For simplicity, let's take this section. Okay. Moving from A to B. From A to B. The distance covered, let's call it dr. dr is the distance covered. The force, well, we know the force. The force is the work needed. So the force, because you are doing the pushing, the force is going to be G, mass of the planet, force is mass of the planet, mass of the thing divided by r squared. Now this is the part that I always get wrong. R is the distance. So r is the distance to here, r. Let's call this capital R, just in case. Yeah, so this is the force. Now you are pushing, because in order to move it with constant speed, you need to be pushing that way. The force is in this direction, because you need to be holding it back, basically. If you want to move it at constant speed, you need to pull it back, otherwise it will accelerate. So force is this way, and the movement is in the opposite direction. So the work done moving from A to B is equal to minus, well, let's do it strictly. It's the movement, it's dr multiplied by the force multiplied by the cosine of the angle between. But the cosine is 180 degrees, because you're moving in this direction. You're moving in this direction, but the force is in this direction, so it's 180 degrees. So it's going to be dr multiplied by f multiplied by cos 180 degrees. Yes, thank you for the annotation. How do I delete that? Okay. dr cos 180 degrees. So it's going to be minus f dr, which is minus g m over r squared dr. And I have a feeling that this is going to be a mistake, but let's see. Right, so the small amount of work done from moving from A to B is equal to minus g m over r squared dr. Now we integrate this part. The work changes from 0 to w, and the integral, and and this the distance changes from infinity to r capital. So we go from infinity to p, and we integrate this part. So this is just w, the work done, and is equal to minus g m open bracket 1 over r squared infinity to r. So minus g m 1 over r squared minus 1 over infinity, which gives you minus g m over r squared. I did not mess it up. I am happy. I usually get the sign wrong because of this. Okay. And the work done is moving is equal to minus g m over r squared. So the gravitational potential energy is now expressed as an absolute value. If you are near a massive object, your gravitational potential energy is minus g m over r squared. So gravitational potential energy, so the answer. Oh, sorry. Yes, of course. So I did mess it up. Sorry. Yes, it's going to be, so the integral of this is going to be, its integral of r to the power minus 2, and that's going to be minus 1 over r. So it's minus 1 over r plus 1 over infinity. Yes, and I remember what the mistake was. Because dr is going to be negative, it's minus dr. dr is negative because we're moving from A to B, we're reducing the r. And this is where there's another minus here. So therefore, you have minus and minus, minus, and another minus. So this is going to be plus. And this is going to be plus, and plus, and plus, and then minus. Okay, and then we have R. Apologies. So minus GMM the integral of 1 over R squared is minus 1 over R. Yes. And exactly. So the answer is gravitational potential energy is minus G M M over R. And let's explore this expression. Gravitational potential energy is equal to minus G M M over R. Well, we don't need R capital anymore. R is just the distance. We can say that, well, this is R, and this is the gravitational potential energy. And it's negative, first of all. And as we approach infinity, it approaches 0. Why is the potential identified as the work done by the force of gravity rather than the work done by the object to be static against the force, thus have potential? Potential energy is not defined as the work done by gravity. Just a second. Yeah, it's the work done by an external force moving an object from infinity to a given point, which is incidentally the negative of the work done by gravity. Because the work done by gravity is positive. It's pulling you down. It's pulling you. So that's that. Right. So it's negative, and then it behaves like this. 1 over R. It's proportional to 1 over R. Interestingly, if you're inside a planet, the gravitational potential does not change. So how does that work? So if for a planet, if you're inside a planet, inside a planet, gravitational field is proportional to 1 to R. Gravitational field is proportional to R. And gravitational potential energy just a second. Yeah. Interesting. Just a second. Ooh, interesting. Interesting. If you are didn't realize that because the gravitational field is the derivative of the gravitational potential. The derivative of the gravitational potential. So derivative of the gravitational potential energy. And that means that the gravitational potential energy inside the planet has to be proportional to R squared. Because gravitational potential energy is the integral of G. Yeah, so if you multiply this by mass, this is the force. Okay, you can say force is proportional to the radius. And force, the rate, so force is also the gravitational potential energy is the derivative of the gravitational potential energy with respect to R. And that is equal to KR. In other words, DE/GPE is equal to KR dr. And if you integrate that, you will get R squared. So in other words, GPE, gravitational potential energy, which is this integral, is proportional to R squared. I won't go very deep into that. I'm just showing you that. So because gravitational potential, because the gravitational field is the derivative of gravitational potential, and gravitational field is linear, therefore the gravitational potential energy is a quadratic relationship. Therefore, inside a planet, I previously said gravitational potential energy is constant. It's not. That's for a hollow shell. So outside, it behaves like 1 over R. It's proportional to 1 over R. But inside, it is proportional to a quadratic. So it's proportional to R squared. So for distances, if you're inside a planet, gravitational potential energy is proportional to R squared. Outside a planet, it's proportional to 1 over R. Quite an interesting feature of the gravitational potential energy. Okay. Then there's quite a straightforward question. Gravitational potential. Gravitational potential is gravitational potential energy per unit mass. So gravitational potential V is equal to GPE divided by mass of the object. So yes, at the center of the planet, gravitational potential energy is 0. Oh, is it though? It's a very good question. That's not possible. Sorry. I must have messed it up. Because it will keep accelerating. It will keep accelerating towards the center. No. Let me think. Let me think. Sorry. Thank you for this question, Andre. Because it keeps accelerating. Sorry. Ignore that. I will let me think about it for a bit. What happens inside a planet? No, it was too simple. I've made a mistake. Gravitational potential is the gravitational potential energy per unit mass. Shouldn't FJR be add up to constant? What's FJR? GB at the surface. Why would there be a potential energy? Look. At infinity, the gravitational potential energy is 0. You think about it. So here's a good explanation. So at infinity, the gravitational potential is 0. At the surface, the gravitational potential is minus 6.2. Because gravitational potential energy is a measure of well, it's how much energy will be converted. Basically, if you fall from infinity, this is how much energy you will gain. If you fall from infinity to the surface. But if you fall from infinity to the center, surely you will gain even more kinetic energy. Therefore, it's not. So if you fall from infinity to infinity, you gain 0 joules of energy. If you go from infinity to the surface, it's 62.72 megajoules per kilogram. That's how much energy you gain. And if you drop to the center, that's even more. So no, it's not. Definitely not. Again, no, it's not. It's not infinity. It's not negative infinity because it can't be. Because this formula assumes that the force becomes infinitely large as you go down. So no, it doesn't work like that. I guess you just need to do the integration and slightly more accurately than I. It's definitely quadratic, but then it goes like this, curves like this, and then something happens at this point. I suspect it's gonna go something like this. Oh yes, yeah. Okay, I remember now. Thank you. Thanks to you, I remember now. So when you are inside, when you are outside the planet, it goes like this. So this is the surface of the planet, R. So this is the planet. So when you are outside the planet, it's proportional to 1 over R. It's negative and proportional to 1 over R. That says R. This is the gravitational potential energy. And inside the planet, it's going to behave like this. It's a quadratic, like this. And the gradient, and why is it like this? Well, because if you remember with the gravitational field, gravitational field goes like this, and then like this. Gravitational field, and this is the radius. So this is R. You have the gravitational field is the derivative of the gravitational potential energy. Is proportional. It's proportional to the gravitational potential energy, dr. And the derivative of a parabola is a straight line. Okay. Yes, you can add a constant to the GP is continuous at R. Exactly. That's how you do it. So the derivative of a parabola is a straight line. That's why it is the gravitational field is a straight line. So I have to stop here. I hope this was somewhat useful. Sorry for messing it up at the end, but I've corrected myself. Problem 7 is fairly easy, and problem 5 is fun. So give it a go on your own, and I'll see you next week. You're welcome.